Good morning, everyone. These are going to be your notes on describing motion. And this whole week, what we're going to be doing is looking at graphs, and we're going to try to understand how to look at a graph and describe an object's motion. So let's get started. So words that describe motion, this whole unit is surrounded around this word kinematics, which we can use words, diagrams, numbers, graphs, equations to describe how an object moves. So kinematics is the study of motion. We already have this in our notes, scalars and vectors. Remember, just as a reminder, that scalars are quantities that are fully described by a magnitude. So this is the value alone. So the number 40 tells us how large that quantity is. Vectors, on the other hand, are quantities that are fully described by both a magnitude and a direction. So remember, we can use east, we can use positive or negative signs to denote direction, we can use cardinal directions, we can say towards Denver or away from Denver, but we need to give a number, a numerical value, and a direction. And then we talked about distance and displacement. And we said distance is a scalar quantity, and it's how much ground an object has covered. It's total distance or total length that it's moved during its motion. And displacement is the overall change in position. So it can move left, it can move right, but how far away from its starting position is it? Displacement versus distance. Displacement is a vector quantity that not only has a number, but also a direction. And that would be the big difference. We talked last week about speed being a scalar quantity. It tells us how fast something's moving. Speed cannot be negative. We only have positive speeds. We said it would be kind of ridiculous to travel at negative 25 miles per hour. And our S equals D over T, when we see that equation, our brain should be thinking this. Average speed is equal to the total distance traveled over the total time it took to travel. So S equals D over T, where D is the total length or total distance traveled. Velocity, on the other hand, and we wrote this equation down, is a vector quantity. And we said that the average velocity is a change in position over time, which is displacement over time. And so both of these equations are the exact same equation. It's just a different way to say position or displacement, or the difference from the starting point. So our velocities can be positive or negative because remember, in physics, the positive and negative sign denote a direction. They are a direction. We got to remember that. We watched a video last week over average speed and instantaneous speed, and if you didn't watch that video, you can pause it and click on the link here and get to that. Hopefully that'll get you there. If not, it is in the week 2 calendar, average speed and instantaneous speed. Instantaneous speed is the speed that is on your speedometer. The average speed would be the total distance over the total time traveled. So looking at all your stops on the way to, maybe you went, you went to go hiking. And so all of the stops you made on the way to your hike in the car, all of the accelerations that you made, it takes all of this account. So the average speed is the average of all of these instantaneous speeds. And remember, on your car, your speedometer is telling us the instantaneous speed, the speed you're going at that moment in time. Okay, so now we get to what we need to write down. So if we take a look here, right, we have a graph that starting at 0, 0 has a positive slope up. So notice how it says the meaning of the shape for an x divided by t graph. This means a position divided by time. And x, okay, a lot of times in physics we denote position in x. That's the variable that is used for the word position, all right? So when we have a straight line on a position time graph, it means that the object is not changing velocity. It's going in the same direction and it has the same numerical speed. It's going 5 miles an hour away from where it started, from the frame of reference. And our frame of reference on a position time graph is our x-axis. So let's just say this object, right, is a car backing out of a driveway. Your house is your frame of reference, so this is the house. The car is backing out of the driveway at a constant velocity. We could give some other examples. It says positive velocity, and so notice how this has a positive slope, and that's why it would be a constant positive velocity. Anytime we see curves in a position time graph, and we'll get to these more as we move along, but curves in a position time graph tell us that we have a changing, this is velocity, and that means it's speeding up in this particular curve. Some curves mean that the object is slowing down. In this case, the object's going from slow to fast, so this would be a positive velocity. It's a positive changing velocity, and we would call this acceleration. Slope. Hopefully we remember that slope is rise over run, and on our position time graphs, the slope is the velocity, because we're taking our y value, which is displacement or position, change in position, and dividing it by time. So if we do that, we get a velocity, right? Like we've calculated this out. We did 2 different worksheets last week where we calculated velocity out. And therefore, if we take the displacement and divide it by the time, we're calculating the velocity. The velocity is the slope. A positive slope means a positive velocity. A negative slope means a negative velocity. Zero slope, meaning a flat horizontal line, means it's not moving, so it has 0 velocity. And if you were to divide y into x, you would get 0, right? All right, our starting position is the y-intercept. I like to think of it as just the entire x-axis would be our, I don't want to say starting position. This should be frame of reference. So please change starting position to frame of reference. I'll do that later. So starting position should say frame of reference. And the reason I say this is because we could start in the positive y, right? So in front of the frame of reference, or we could actually start in quadrant 4, right? 1, 2, 3, 4, in negative y values. So I could start actually behind my frame of reference. I'm going to skip over dot diagrams. We don't need to know this just yet. And I think that's it. So those are the 2 big ones. So I'm going to stop here, and hopefully you've gotten all that down. If not, please pause the video, go back, and get down whatever you need. Great.